Today we want to talk about trigonometric identities, but we do want to remind ourselves of where we were. We were talking about this unit circle. We want to take our iconic triangles, the 45, 45, 90, and the 30, 60, 90 triangles, and put them into a unit circle. That's a circle of radius 1. We want to know everything going around the circle. We know that this is at 0 degrees. This is at 0 degrees, and the coordinates of this point are 1, 0. We have down over here 180 degrees with coordinates of -1, 0. Up here at 90 degrees, we have coordinates 0, 1. Down here at 270 degrees, we have coordinates 0, -1. We want to learn the unit circle going all the way around from 0 to 360. We are currently in the process of learning the unit circle from 0 to 360. All the coordinates of all the angles with reference angles of 30, 45, and 60 degrees. So I want 30, 45, and 60 in each of the 4 quadrants. I want the quadrant angle 0, 90, 180, and 270. And we want the coordinates going all the way around, because the coordinates of each of these points are the cosine and the sine of the angles at those locations. What I want to remind us of is how we can find the 30, 45, and 60 degree angles. So the other things that we want to remember is that the coordinates are cosine theta and sine theta. The coordinates of each of these points on the unit circle are cosine theta, sine theta. We'll have to do a little extra work to get tangent of theta, but for now, we're going to learn cosine theta and sine theta going all the way around the unit circle. 30, 45, 60 in all 4 quadrants, and the angles on the quadrant, or on the axis. We want to make sure that we associate cosine of theta with the x coordinate and sine of theta with the y coordinate. This goes with the stuff we saw earlier, where we said sine of theta is y over r, cosine theta is x over r, and tangent of theta is y over x. On a unit circle, r is equal to 1. So sine of theta is y, cosine of theta is x. This will help us remember what's positive where. Sine is positive when y is positive. That's quadrants 1 and 2. Cosine is positive where x is positive. That's quadrants 1 and 4. Tangent is positive where x and y have the same sign. That's quadrants 1 and quadrants. So here's how to properly locate your 30, 45, and 60 degree reference angle. Whatever your radius you use, that's going to be 1. And you want to make sure you can find the half radius. So you draw a circle and then you mark off where half the radius is. When you go horizontal and find where y is equal to a half, that will show you your 30 degree reference angles. Now I'll show the points on the unit circle that will correspond to a 30 degree reference angle. y equals plus and minus 1/2 corresponds to 30-degree reference angles in all four quadrants. So when y is equal to 1/2 plus or minus 1/2, that corresponds to a reference angle of 30 degrees. Can't draw the other one from that side of the table. Okay, this is the same side. I have to come from this angle. We want to associate 30, we want to be able to put 30 degrees in all four quadrants. In quadrant 1, 30-degree reference angle is just 30 degrees. What is it in quadrant 2? What's this angle here with a 30-degree reference angle? 150. What's a 30-degree reference angle in quadrant 3? 210. What's a 30-degree reference angle in quadrant 4? So you go for y plus or minus 1/2. That's how you locate your 30-degree reference angles. For your 60-degree reference angles, you're going to locate where x is plus and minus 1/2. So when x is plus and minus 1/2, that's where you're going to find your reference your 60-degree reference angle. And we should know our 60-degree reference angles in all four quadrants. I'll do the hard one. First quadrant, 60-degree reference angle is 60 degrees. Okay, maybe that wasn't the difficult one to remember. What's a 60-degree reference angle in quadrant 2? 120. 60 degrees in quadrant 3. 240. 60 in quadrant 4. 300. We want to know the coordinates of all these points. So we want to identify that at this 30-degree angle, we have coordinates. We know that we got this by finding the y-coordinate of 1/2. And we got the 60-degree angle. We got these coordinates. I'm gonna put something where x is equal to 1/2. We want to remember that if one of the coordinates is a 1/2, then the other coordinate will be a square root of 3 over 2. because that's one of the other values that we have. This is supported by remembering that that co-functions of complementary angles are equal. So the sine of 30 is equal to the cosine of 60. Co-function, sine and cosine, complementary angle, 30 and 60. They come from the same triangle. What's opposite the 30-degree angle in the 30-60-90 triangle is adjacent to the 60-degree angle in the 30-60-90 triangle. The last one that we'll want to place, the last four, I guess, that we'll want to place are the 45-degree angles, and they're going to be halfway between the 0 and the 90, or halfway between the 30 and the 60. To locate those, we'll just go along the line where x and y are equal. So we'll start at 0, 0. Here's 1, 1. Just kind of aim through that point. Just aim through the point where x and y are equal or x and y are opposites. So 45 degrees in the first quadrant is just 45 degrees. What's 45 degrees in the second quadrant? 135. What's 45 degrees in the third quadrant? 225. And 45 degrees in the fourth quadrant? 315. We want to remember that the 45-degree angle happens when x and y are the same. We just have to remember the value. What's the value for cosine and sine of 45 degrees? Root 2 over 2. Now all we have to do is get the signs in order, with the signs lined up for each of the other quadrants. The 60-degree reference angle, the values will be 1/2 for the x and root 3 over 2 for the y. But in the second quadrant, cosine is negative, x is negative 1/2, and y is positive. Y is positive root 3 over 2. So we can take these 3 points. Once we know that first quadrant, we just get the signs correct in the other 4 quadrants, and we've got the whole thing going around. If this seems like a lot to remember, that's only because it's a lot to remember, and I want you to remember all of it all the time in perfect detail and instantly, from now until the end of time. It's like your trigonometry times table, learning the unit circle going all the way around for your iconic triangle, your 30, 45, and 60-degree reference angle, and the angles on the quadrants. Like we've talked about before, it really isn't a lot to remember. Instead of sitting down and trying to memorize this, look for the patterns that I don't have a phrase for it. Look for the patterns that make sense to you. Look for the patterns that you vibe with. That's how you ruin a word. Just take old people and start using it. So if there's any words in the young person's lexicon, you say, oh man, I hate that phrase. I need to get rid of it. I'm going to have Leach start doing it. Just have Leach start doing it, and it will go away. It's like, old people are doing it. Next thing it's going to happen is going to show up on Facebook, and then it's done. Once the trend shows up on Facebook and the minion moms start doing it, it's done. It's all over. It's no longer true. Comment? Snide remark? Look for the patterns to remember where these points are associated with their angle. Draw this a few times. Fill in all the coordinates going all the way around the circle, and you will not be able to forget it. So over here, the points where x and y are equal. Actually, there are two lines. There's the positive slope one, x equals positive y, and x equals negative y. I'm going to write them down like equations of lines. So y is equal to plus or minus x. Then your reference angle is 45 degrees. The other thing that we want to point out that we hadn't pointed out yet is the number of sectors that each of these angles divides 360 degrees into. Notice that the 60-degree angle has 6 sectors: 0, 60, 120, 180, 240, 300, and then 360. 160, 260, 360s, 460s, 560s, and 660s. There are 6 sectors. 30-degree angle divides the 360 into 12, because 360 divided by 30 is 12. So there are 12 sectors for 30 degrees. Because the 60 is also 2 30s, 90 is 3 30s, so 130, 2 30s, 3 30s, 4 30s, 5 30s, 6 30s, 7 30s, 8 30s, 9 30s, 10 30s, 11 30s, 12 30s. 12 sectors. The 45-degree angle divides the circle up into 8 sectors. The 4 quadrants cut in half. Here's 145, 2 45s, 3 45s, 4 45s, 5 45s, 6 45s, 7 45s, 8 45s. So there, the 45-degree angle divides the circle up into 8. 30-degree angle divides it into 12. 60-degree angle divides it into 6. How's everybody okay? It's the unit circle again. If you're like thinking, didn't you do this on Thursday? Yes. Guess what we're going to lead with on Thursday this week? Because songs don't get stuck in your head if you hear them one time. Songs only get stuck in your head when you hear all of them. I wouldn't have to do this every day in class if we didn't just meet twice a week. But they're like, oh, you're not allowed to implant memories into students' brains when they're not at school. And I'll just subconsciously send this through like the white noise that you use to sleep to. Some of you are like, well, I don't sleep to white noise. I'm like, oh, I'm just kidding. I'm not allowed to do that anymore. How's everybody okay? So we want to make sure that we know the unit circle going all the way around. One of the things that we've noticed based on observing the unit circle all the way around in all of its gory details, is that a lot of our trig functions are related to each other. Sine is y over r, cosine is x over r, tangent is y over x. So that means we could take tangent and find tangent by doing sine over cosine. Y over r divided by x over r. The over r cancels out and we get y over x. So a lot of the trig functions are related. Cofunctions of complementary angles are equal. A lot of our trig functions are related. Look how much we're filling out with just 0, a half, root 2 over 2, root 3 over 2, and 1. We get the coordinates of all these points with plus or minus 0, half, root 2 over 2, root 3 over 2, and 1. Plus and minus going all the way around the circle. I know plus and minus 0 is a little bit weird, but I needed the plus or minus. And so today we want to look at trigonometric identities. An identity is just a type of equation. An identity is an equation that's always true. X equals X. That's an equation that is always true. An equation that's always false is called a contradiction. Zero equals 1 is a contradiction. That is never true. Better yet, something with a variable in it. X is never equal to X plus 1. An equation that's always true would be something like X equals X. A number is always equal to itself. That's an identity, an equation that is always true. A contradiction is an equation that is never true or always false. In between, you have equations that are true sometimes. Those are conditional equations. An equation that is sometimes true is conditional. Two x equals 10, but only when x equals 5. That's the condition that makes the equation true. That's what we used to call DVD bonus material, and is only available in the director's cut. This is the director's cut of this class. I'm the director. The regular cut of this movie is only like 2 hours long. The director's cut is, let's see, 5 hours a week times 17, 85 hours long. What you were looking for is the theatrical release. That one's not available. So we want to learn some trigonometric identities, and then we want to learn some things that we can do with those trigonometric identities. Trigonometric identities come in categories. The first category we're going to have is reciprocal identity. We already know these. Sine of theta is 1 over cosecant theta. Spelled S wrong. Sine of theta is 1 over cosecant theta. Cosine theta is 1 over secant theta. Tangent theta is 1 over cotangent theta. These are reciprocals. One of the things you can do to both sides of an equation is make reciprocals of both sides of the equation. So I flipped these over. We can write these also as cosecant theta is 1 over sine theta. Secant theta is 1 over cosine theta. And cotangent theta is 1 over tangent theta. We had previously listed associated sine, cosine, and tangent with coordinates. So we might write cosecant as r over y. Secant we could write as r over x, and cotangent as x over y. Just the reciprocals of the coordinates that we had above. So for example, we know that the sine of 60 degrees is square root of 3 over 2. So cosecant of 60 degrees is 2 over square root of 3, the reciprocal. We might want to rationalize this. Say if we're doing homework on Canvas or something, so we're going to multiply by root 3 over root 3. And write this as 2 times the square root of 3 over plane 3. Reciprocal means multiplicative identity. That just makes it worse. Reciprocal means flip the fraction over. Six reciprocal identities only counts as 3. Still only counts as 3. How's everybody okay? I'm just data entry today. It's like, if I could just type this and email it to your brain, then I would. But I'm not allowed to do that anymore. I'm like, well, no more psychic emails. So the reciprocal identities are really just how we define secant, cosecant, cotangent. That one kind of goes in circles. Ratio identities actually start establishing relationships between trig functions. So like the ratio identities say the following: tangent of theta is sine theta over cosine theta. And since the cotangent of theta is 1 over the tangent of theta, cotangent of theta is cosine over sine. If this is 2 times as many things as you want to remember, tangent of theta is sine over cosine, that's the one to remember. So like we saw in our unit circle, here are some values that we know. Sine of 120 is √3/2. And cosine of 120 is -1/2. We know it's √3/2 because 120 is 60 degrees in the second quadrant where sine is positive. Cosine will be negative in the second quadrant. So we see that 120 and we think this is 60 degrees. In quadrant 2. So these ratio identities are going to combine with the unit circle that we have to give us the values of tangent. We just take the y coordinate divided by the x coordinate. So this will tell us that tangent of 60, or sorry, tangent of 120 is sine of 120 √3/2 over cosine of 120 -1/2. √3/2 divided by -1/2. We can cancel out the over 2. √3 over -1, -√3. This makes sense because we know that the tangent of 60 is √3 and tangent is negative in quadrant 2. We always got to make sure that our answers make sense. Tangent of 60 is √3 and tangent is negative in quadrant 2. So negative √3 makes sense. We can also check 120 tangent negative square root of 3. Like, are you sure about that? Let's square it. 3. So that was the square root of 3 that we were looking at. Any questions? Is everybody okay? Finally, our third class of basic identities that we always have to remember from now until the time are Pythagorean identities. This is the Pythagorean identity. This is the one Pythagorean identity that you have to remember. Cannot escape this Pythagorean identity. There, question? Good question. Cosine squared theta means the cosine of theta squared. So the when we write cosine squared theta, we mean the square of the cosine of theta. This is a notation that we picked, so we wouldn't have to write so many parentheses. Like I was there. This is a notation that was chosen, so we wouldn't have to write so many parentheses, but that's what that means. So cosine squared theta. This is shorthand for cosine of theta then squared. Notice that it's the square of the cosine of theta, not the cosine of the square of theta. I don't know if that helps or makes it worse. It's fucking English just messes everything up. Terrible language for math, but word-wise, we'd want to say the square of the cosine we'll find the cosine first and score the result. The reason that we call these Pythagorean identities is that they are based on the Pythagorean theorem. If we pick a point on our unit circle, if we pick this point on the unit circle, then the hypotenuse is 1. The adjacent side is x. The opposite side is y. In this scenario, the cosine of theta is x over 1. The sine of theta is y over 1. Cosine of theta is x over 1. Sine of theta is y over 1. Which gives us x squared plus y squared is equal to 1. That's the equation for a unit circle. The sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. So if we start with x squared plus y squared equals 1 squared, we trade x in for cosine, y in for sine. We get cosine squared theta plus sine squared theta is equal to 1. This is actually 3 identities that we don't always want to explicitly write, but we want to recognize, so I'm going to explicitly write them down. So cosine squared plus sine squared is equal to 1. Variation of this would be that cosine squared theta is equal to 1 minus sine squared theta. That's just rearranging a plus b equals 1. Then a is equal to 1 minus b. I can rearrange this for sine in the same way and say that sine squared theta is equal to 1 minus cosine squared theta. So this is just a rearrangement of our original one. If you know the first one, these other two just follow from that. This is just us understanding the relationship between addition and subtraction. Here's another way that we can rewrite this identity. I need more space. Do you mind? I can take this identity, cosine squared plus sine squared is equal 1, and divide by cosine squared and get a relationship between tangent and secant. So here's another Pythagorean identity. 1 plus tangent squared is secant squared. Exploiting the relationship between addition and subtraction, we could rewrite this one in two different ways as well. I know you're all thinking, please don't. Michael, oh, yeah, we are. But I'm not going to do the one where we divide by sine squared. I can rearrange this and say, instead of saying secant squared is equal to 1 plus tangent squared, I could say tangent squared is secant squared minus 1. I can also say secant squared minus tangent squared is equal to 1. We can also take this cosine squared plus sine squared equals 1 and divide by sine squared to get a relationship between cotangent and cosecant. But I'm not going to write that one down. We don't care about that one. In the cosine squared plus sine squared equals 1, and the 1 plus tangent squared equals secant squared. Cosine squared plus sine squared is equal to 1. That is Marcia. What's the little kid's name? Jan is in the middle, in the Brady one. Marcia, Jan, and Cindy. So cosine squared plus sine squared is equal to 1. That one's Marcia. 1 plus tangent squared equals secant squared. That one's Cindy. This one is Jan. I didn't even write it down. Otherwise, when I do write it down, it's just like, oh, Marcia. But in this case, it'd be like, oh, cosine squared plus sine squared equals 1. Cosine squared plus sine squared equals 1. Cosine squared plus sine squared equals 1. And it gets very annoying. Just keep going. Any questions? That was a lot of exposition. Let's take a break. Come back and have an action sequence. Just